I will give a more familiar case of the parallel postulate in the Euclidean geometry. Of course, you are familiar with the axioms of the Euclid, and one axiom is parallel postulate. One easy version of parallel postulate is that if you take any line, straight line, and if you take a point outside that, then there is one and only one line parallel to this line passing through this point. That is the parallel postulate of Euclid. Of course, Euclid used other axioms, but most of the other axioms are not like this, more simpler. So many people, even it is heard that even Euclid had this doubt that this is not an axiom, this is just like a theorem, more complicated. What is the problem? ഒന്ന് പറയും, ബബീഷിനോട് പറയാം, അല്ലെങ്കിൽ നിങ്ങൾ ചെയ്താൽ മതി. ടെമ്പറേച്ചർ അഡ്ജസ്റ്റ് ചെയ്യാം. 25, 26. So, people were suspicious about the parallel postulate. Some people feared that parallel postulate is not a postulate, not an axiom, but it is a theorem. And that theorem can be proved using the other axioms. There was a general feeling people had. And mathematicians, of course, great mathematicians, tried to prove this theorem, prove the parallel postulate using the other axioms. Nobody could prove it. Then people tried to disprove this axiom. People tried to disprove the statement using the axioms of the other axioms of the Euclidean geometry. What happened was that both these people failed. People were not able to prove this statement, and people also not able to disprove this statement. That is, in an axiom system, this Euclidean geometry is an axiom system. Of course, you take, suppose Euclidean geometry is the axiom system E, you delete the parallel postulate, the new axiom system, I am calling it E dash. That is Euclidean axiom system except the parallel postulate. You take this axiom system, and suppose P is the parallel postulate. In this axiom system, P cannot be proved, and in this axiom system, P cannot be disproved. That is what happened. And this problem was ultimately solved by the introduction of non-Euclidean geometries. The non-Euclidean geometries are geometries where all the other axioms of the Euclid are valid, but parallel postulate is not valid. There are hyperbolic geometries as well as elliptic geometries. For example, you take this surface of the sphere. In the surface of the sphere, the lines are great circles. There it happens that any two great circles intersect at 2 points. So that we cannot get parallel lines. In the hyperbolic geometry, it happens the other way. Given a parallel line and a point outside that, we can find more than one lines passing through that point, but parallel to the given line. So this is an example of a statement which cannot be proved and which cannot be disproved. In the history of mathematics, the case of axiom of choice and the continuum hypothesis was this was similar. It was proved that the continuum hypothesis and the axiom of choice, these two statements cannot be proved in the set theory, and it cannot be disproved in the set theory. And if something cannot be proved and something cannot be disproved, what is the only option available to you? You can either believe it or not. That position you can take. Because you cannot prove it, you cannot disprove it also. So the only problem is, the only choice you are having is to add that also as an axiom of your system, if you like. Or you need not take that axiom. But of course some questions will be unanswerable. So, such big philosophical problems are at the roots of the set theory. So this is one importance of the set theory. And of course, we are having how many? 1 or 2 philosophy students? How many philosophy? You are from philosophy. You? Philosophy. I said, at least we are having 2 friends from philosophy. And this is a big reason for philosophers to be interested in set theory. Of course, there is another thing also. There is something called infinity. Mathematics students will think that infinity is something related to mathematics only. Even in mathematics, infinity is a big problem. But in philosophy, infinity is a bigger problem. And one of the accomplishments of Georg Cantor in creating set theory is to give an approach to manage infinity, in at least in some cases, beautifully. And for the very reason this work of Cantor was objected by the greatest mathematicians of that time. So the problem of infinity is a very big problem in philosophy as well as mathematics. So we'll be considering some of these things during the course of this lecture. So this is the relevance of set theory from the philosophical point of view. I would rather say that set theory is one of the greatest accomplishments of human mind. I'm not the first person to say that. Of course, this is a quotation from whom I don't know, but of course there are several people having this. It is one of the greatest accomplishments of human. So we should celebrate that. Humanity, which started from African forests, their life with some small equipments made out of stone. That is the place where the journey of human beings, Homo sapiens, started. And now we are here. And if you look at the history of the thought of Homo sapiens, I think set theory is having a great place. It's one of the greatest accomplishments of human mind. And that is a big reason why I'm keen on spending my time as well as your valuable time on this topic. Okay. So you may be thinking why this man is giving such a very long introduction The reason is that my feeling is that this lecture series is not to be over by the end of May. My feeling is that it should be continued further, and for such a long lecture series, I feel that a sufficiently long introduction should be there. Of course, you may ask, suppose we want to study set theory, which books do you suggest? Here's one example. Schwamm's outline of set theory and logic, set theory and related topics. Schwamm's outline of set theory and related topics by Seymour Lipschutz. I think mathematics and computer science students will be familiar with the Schwamm series books, and there is a set theory book, and I recommend that as a place to start with. You can, but of course, to those who are familiar with the basics of set theory, there is a good book that is also my favorite, Naive Set Theory by P.R. Halmos. P.R. Halmos is one of the famous mathematicians, and of course he is no more, and famous textbook writer. He had written several very good textbooks in pure mathematics, and this is one of my favorite books in set theory, Naive Set Theory. But this is slightly more sophisticated than Schwamm series set theory book, because Naive Set Theory is slightly more axiomatic than Schwamm series. So for a beginner, Schwamm series of set theory will be useful, and after completing that, they can start with Naive Set Theory. And even Naive Set Theory is not very axiomatic. There is another book by Davelin. The name of the book is Contemporary Set Theory. Name of the book is Contemporary Set Theory. There is another book by Stoll, Set Theory and Logic. That is by Stoll, and there is a textbook for our MPhil mathematics course as well as PhD coursework, research methodology. Of course, there are several other interesting textbooks. I will be giving the names in the course of the lecture, and also I will be putting such useful data in my personal website, www.ramachandranpt.in, where you can get the latest information about this lecture series, and I will put more references there. So that is about the references. My website also gives other recommended books also in other areas also. You can use that. Now, people say that Georg Cantor was the father of set theory. That is the general trend. Every subject should have a father, not mother. I don't know. So set theory should have a father, and people say that Georg Cantor, a German mathematician, was the father of set theory. who was Cantor. His full name is Georg Ferdinand Ludwig Philipp Cantor, 1845 to 1980. His birth was on 3rd March 1845 at St. Petersburg in Russia. His parents were Danish they were from Denmark originally, and both were, I think, of Jewish origin. His father was converted to Protestant Christianity, and the mother was, I think, born as a Catholic. Even though he stayed there in Russia for some time, later the family migrated to Germany. Cantor studied in Berlin, Zurich. For a brief period he was in Göttingen. He had taken his PhD in the theory of numbers in 1868 from the University of Berlin. His PhD thesis was on the Diophantine equations like this: ax square plus by square plus zz square is equal to 0. A, B, C are integers, and we have to find integer solutions x, y, z so that this is true. This is the study of such systems, such equations are called Diophantine equations. That's a important part of number theory, and a commendable work was done by Carl Friedrich Gauss, the prince of mathematicians. And in fact, Cantor continued the work of Cantor on some of the things related to the solution of integral solutions of this equation. Of course, it was accepted by one of the best universities in Germany, so it should be a fairly good thesis. But many people say that it is not that illustrious and not comparable with the work of Cantor. Later that. Even though he started with the number theory, he later changed to other fields also. He had a friend, Hein, who was interested in the study of trigonometric series. So what is a trigonometric series? I think everybody are familiar with Fourier series. Trigonometric series is slightly more general, because we are not assuming that the coefficients are obtainable as that integrals. That is this trigonometric series is something like this. Say a naught plus sigma n is equal to 1 to infinity a n sin nx plus b n cos. If the a_n's and b_n's are defined by that equation, then it's called Fourier series. But here we are not assuming anything about a_n's or b_n's. So this general thing is usually called trigonometric series. The only difference is that for Fourier series, we assume that a_n's or b_n's are obtained as integral f of x into sin x in x, etc. But here we are not assuming that. This is more general thing. So these people were interested in the case of functions which can be represented in this form using a trigonometric series, not necessarily Fourier series. Okay, suppose f is a function. Can you write that function as a trigonometric series in this way? Of course, all functions cannot be written this way. And suppose a function can be written in as a trigonometric series in this way. Is that representation unique? The question is whether there is this function is written as a trigonometric series like this. That means the right hand side is a series. For every value of x, this series converges to f of x. That is what we mean by that. The question is whether there is another such trigonometric series. Say a naught dash plus summation n is equal to 1 to infinity a n dash sin nx plus b n dash cos nx. This is another trigonometric series which also converges to the same f of x. Then can you say that these two trigonometric series are one and the same? Two trigonometric series are one and the same means all an's are equal to the corresponding an dash and all bn's are equal to the corresponding bn dash. Then we say that these two trigonometric series are the same. So suppose so there can be two cases. Either if a function is represented as a trigonometric series like this, that representation can be unique, which means if you represent it in another way, the corresponding coefficients are same. There is one possibility. The other possibility is that the same function can have two different representations as trigonometric series. That is, in both the representations there exists at least one coefficient which varies. This was a problem. Of course, I think this problem was suggested to Cantor by his friend Hahn. The Hahn-Boll that he was a friend of Cantor. Then Cantor proved a theorem. Actually, Riemann, one of the greatest mathematicians ever lived, and several other great mathematicians tried to prove this theorem. And it was proved by Cantor in 1870. In 1870, Cantor proved that this is the case. That if a function is represented as a Fourier series throughout the real line, this is for every x. Suppose this is true for every x element of R, then the corresponding coefficients are one to same. That was proved by Cantor. That was a great result proved by Cantor. Of course, this problem is equivalent to another problem. Suppose there are two such representations. Suppose what happens when you subtract one from the other? You will get something like this: a naught minus a naught dash plus sigma n is equal to 1 to infinity a n minus a n dash sin nx. And this difference will become constant function 0. So this problem is equivalent to proving that if you are having a trigonometric series representing the constant function 0, then all the coefficients are 0. So in order to prove this theorem, we can prove an equivalent theorem which states that whenever a trigonometric series like this converges to 0 at every point of the real line, then all the coefficients are 0. So this was what Cantor proved first. For this, we need the assumption that this convergence is there at every point of the real line. Later, Cantor tried to improve things. Suppose there is one point. At that point, the convergence is not there, but all other points we have convergence. Then also, Cantor was able to prove this theorem. Later, he improved. If you delete a finite number of points from the real line, for the all other points, if you have convergence like this, if they converge to 0 at all points except a finite number of points, then also we can prove that all the Fourier coefficients, all the coefficients a n and b n are 0. Then Cantor was trying to improve his results further. There is if you have convergence at all points, good. If you have convergence at all points except one point, that is good. If you have convergence at all points except a finite number of points, then also it is good. Then what is the next question? What happens if you delete an infinite number of points? Then he did something like this. You take a sequence a0 less than a1 less than a2 etc. less than a minus 1, a minus 2 etc. So that as you goes this side, this converges to minus infinity, diverges to minus infinity, and an goes to plus infinity. For example, you take the set of all integers. Suppose you take a0 is equal to 1, a1 is equal to 1 etc. So on one side that goes to minus infinity, on the other side it goes to plus infinity. If you take such a set of infinite set of real numbers, and if you have convergence at all points except at these points, then Cantor proved that all the coefficients are 0. So in addition to removing finite number of points, you can also remove infinite number of points. But you cannot remove any set. So he was interested in determining those subsets of the real line which when deleted will not obstruct the proof. That is, he gave a definition like this. Suppose D is a subset of real line. D is a set of uniqueness if the trigonometric series, that is a naught plus sigma n is equal to 1 to infinity a n sin nx plus b n cos nx converges to 0 for every x in R minus D, that is for all points other than those in D, then the coefficients a naught, a n and b n all are 0. Such a set of real numbers is called a set of uniqueness. So what Cantor proved first was that empty set is a set of uniqueness. Then he improved that singletons are sets of uniqueness. Then he proved that finite sets are sets of uniqueness, and then he proved that infinite sets like this mentioned earlier, that is A naught, A1, A2, A3, etc., A minus 1, A minus 2, etc., where as n tends to infinity, an tends to infinity, and when n tends to infinity, a minus n tends to minus infinity. Such sets are sets of uniqueness. So the question is, what are all the sets of uniqueness? We should have a vague feeling that if a set is substantially small, it will be a set of uniqueness, because if A is a set of uniqueness, then all subsets of A are also sets of uniqueness. Then Cantor found out another interesting thing. Suppose P is a set of real numbers. P is a subset of real numbers. We have the concept of a limit point. X, a point of the real line, is a limit point, means if you take any small neighborhood of x, that is you take some x minus epsilon to x plus epsilon, some open interval, that interval contains infinitely many points of P. That is the definition of a limit point. Some people call the same thing accumulation point, other end point, limit point, several names are. Now, you take the set of all limit points of P. Say, call it a P dash. It is usually called the derived set of P. If you take a set of real numbers, the set of all limit points of that set is called the derived set of. Now, for every set of real numbers, there is a derived set. Cantor observed that if P dash is a set of uniqueness, then P is so. So there is something related to this concept. Then he tried to iterate this process. That is, suppose you start with a P. Call it P0. Then P1 is defined as the derived set of P. P0. That is the derived set of P. Now, the process can be continued. We can take P2 as the derived set of P1. And P3 can be defined as the derived set of P2. P4 can be defined as the derived set of P3, etc. So you can go on doing this. Take the derived set, take the derived set of the derived set, derived set of the derived set of the derived set of the, etc. So there is no limit. You can go on doing this. And if after a stage this becomes finite or empty, such sets are obtained as sets of uniqueness. But the limitation of the mathematics of that day was that you cannot continue further. That is, if you are given a set P, you can take the derived set of that, then take the derived set of the derived set, again. How many times you can repeat? Any finite number of times. For that you can define P0, P1, P2, etc. in general, Pn, where n is any positive integer, however large that may be. But you cannot proceed further, can you? No. At that time, we could not proceed further. But Cantor was different. Cantor had the courage to proceed further. That such mathematical courage is the greatest gift creating a great mathematician. He thought like this. He took the intersection of all these sets, P1, P0, P1, P2, P3, etc. He took the intersection of all these things. Actually, let me denote that P omega as the intersection of all Pn. N varies from 0 to infinity. That is, all points which are in Pn for every n. N starting from 0 to infinity. Actually, this was not the symbol he used. I think he used, I don't remember, 0 or omega, some not the symbol, but some other symbol. But this is the modern standard notation. That is why I am using this. But the symbol is not important. The concept is important. So we can define now. Then he defined P omega plus 1. Actually, I am not using his notation, but the modern notation. This is the derived set of P omega. What is P omega? P omega is the intersection of all P0, P1, P2, P3, etc. And once you get P omega, you can take the derived set of that. And that is P omega plus 1. And if you can do that, the next step is clear. P omega plus 2 is derived set of P omega plus 1. In this way, you can define P omega plus n for any positive integer n. So we'll be having P omega plus 2, etc., etc. And if you take the intersection of all these sets, you will be getting another set which is P omega plus omega. No doubt. P omega plus omega, you can call it say omega 2. And P omega 2 is a set, you can take the derived set of that, call it P omega 2 plus 1. Then P omega plus 2, omega 2 plus 2, etc., etc. Go on doing. And taking the intersection of these sets, you will get P omega plus C omega 2 plus omega, P omega 3. You can go on doing this. Once you get P omega 3, you can take the derived set to get P omega 3 plus 1, etc., etc. Omega 2, omega 3, omega 4, etc., etc. You create P omega 2, P omega 3, P omega 4, etc., etc. You take the intersection, what will you get? You will get P omega omega. And P omega omega can be abbreviated as P omega square. Of course, derived set that can also be taken. Go on doing that. And what are these superscripts? They are nothing but the Hodel numbers created by Cantor as a generalization of positive integers, non-negative integers. That was one of the greatest accomplishments of Cantor. And the study of the unique sets of uniqueness of trigonometric series is the motivation for this one.